Good morning. Welcome to the lecture on hybrid recommendation approaches. So the question is, why would we need more than a single type of approach to building a recommender system? What are those architectures for combination, and how might we go about evaluation, although here it gets rather fuzzy and imprecise. So why ensembles work really is related, if we wish to describe a very simple model, to the idea of Bernoulli trial. So what we're trying to do is combine a number of what we consider to be independent opinions. I imagine them to be domain experts, such that we can come up with a best solution. This is why very often we come up with multiple opinions when we're performing diagnosis, because we're not sure if one on its own will be correct. We'll very often, in the case of a stock portfolio, look for multiple assessments. So let's imagine something. The first thing we'll assume in any model, any independent recommender system, is that all of the underlying opinions are independent. Now that's clearly a gross assumption, but much as we've been doing with the use of naive Bayes, often that provides us with pretty reasonable results. So let's imagine that we've got 5 independent classifiers. So the models have been derived independently, the assumptions are completely different. And what we're looking for is a majority voting outcome. So that's equivalent to a Bernoulli trial, where what we're looking for is, if we assume that each one is 70% accurate, then we can calculate that by looking at the formula that's the second sub-bullet that starts with 10. So we're actually using the n of k, p to the power k, q, n minus k. So we see that we've got for 3, 4, 5, we've got 3 terms. So it's 10, 7, 0.7 to the power 3, 0.3 to the power 2, plus 5, 0.7 to the power 4 times 0.3, plus 0.7 to the power 5. And those are 3 terms in that Bernoulli distribution. So we've used n and k for 3, 4, and 5 respectively to compute the probabilities of having 3 agree, 4 agree, and 5 agree. And if you do that calculation, that gives me an 83.7% majority vote accuracy. So we can see that given the assumptions that we've just set up for ourselves, namely 70% accuracy for each classifier, each recommender, and 5 independent recommenders, then the accuracy, the correct thing to be recommended, is going to be 83.7. We can go further and compute the number of classifiers we would need to get 99.9. And that can be a simple calculation of performing that sum of p of k over a very large value of n, where it's n over 2 plus 1. We want that value summed to be, in this case, 0.999, 99.9, and we can play with the value of n, and for this particular case, where the accuracy of each recommender / classifier is 70%, we would need 101 independent classifiers. So this is a reasonable way of evaluating how we would come up with a number of independent classifiers. And it's often quoted as the reason why we use ensembles. Also, I've put a project report on the projects page which refers to the assessment of ensembles in a particular domain. And there's a link on the projects page if you want to look at what was done for, in that case, an honours project some years ago. So why does it work? Well, here what we've got is we want to predict that something is an elephant, and really there are, in this case, 6 distinct models, but each model really understands part of the domain, and you can see that model 1 really understands what a trunk is, model 2 understands what the tusks are, model 3 the ears, 4 the actual feet of an elephant, 5 the actual body of the elephant, and 6 would be the tail. So that elephant represents some unknown distribution, and if we sample from the right part of it, one model as opposed to another will actually be more accurate. Not every model is accurate in all parts of the domain of the underlying distribution. So the ensemble gives me that global picture. No individual recommender system, no individual classifier understands the entire thing. And that's the point we're getting across here. So the purpose is to overcome limitations of each individual underlying model. So one part is interested in some sub-region, some subdomain of the actual data. And we're approximating across the entire domain for that model, even though it's inapplicable. So we're doing some kind of model averaging. So if we were to build some kind of association rule-based model, it would give us that kind of accuracy where we see that the decision boundary, which has been obviously constructed to give us a nice model here, isn't well represented by the underlying decision tree or association rules. It doesn't matter what we're really referring to here. Association rules are a different form of decision tree that can equally represent it. But if we do some kind of averaging across the usage of multiple models, we can more accurately represent the decision boundary. If you remember, the clusters in a cluster-based model of some underlying data, it's the boundaries that you compute between the clusters which are the things which are most important. It's the data at the boundary or close to it which are the most important things. When they flick over from one domain to another, that's where we change significantly the accuracy or recall of the system. So we're interested in getting close to that boundary. That's what we're trying to achieve. So hybrid recommender systems then are just an attempt to create multiple classifiers, if you will, from various domains that more accurately allow us to predict or generate recommendations that will meet a user's needs. So we might put together multiple recommenders designed around a user's profile suitably abstracted. So, for example, taking into account demographic type of information as opposed to things that are latent for the domain itself. We might use social information, such as I've asked you to do with respect to the suggest algorithm. In assignment 2, we might use a model derived off of product features So dimensions that are explicitly represented in the underlying data. And then finally, we might use knowledge models, if then else rules, association rules, possibly decision trees, things not studied in this particular course. But we might actually generate multiple models associated with those 4 distinct types which were introduced right in the very first lecture on recommender systems. So at the end, that recommendation component could take all of those models derived from those 4 distinct types of data in a particular form, as we shall see, a particular processing architecture, and to generate a recommendation list. From the user's perspective, the recommendation component is still a black box. But now what we're doing is looking at that black box as having more structure. So in a real system, you will have all of the above. Collaborative filtering, content-based filtering, knowledge-based, and social, as we've talked about before. And the reason that we might, one of the very distinct reasons why we might include something very early on is this idea of a cold start problem where we've got no recommendations. So we might actually derive those based upon some very simple model which we've come up with based upon a domain expert, somebody who knows shopping, if you will. So hybrid, indication here of combination of many things that come from, that have essentially a special component to a different, coming from a different part of a taxonomy. But the goal here is ultimately to improve recommendation performance, satisfaction of the user in getting lists of recommended services or products that meet their needs. So we can talk about a number of different hybridization strategies, multiple simultaneous or concurrent use of systems. We can talk about a single box, but internally using different features such as demographic and non-demographic information. And we could talk about a pipeline now of use of different systems. And we're just about to go and describe all of those. So let's imagine we deal with the monolithic first. And here we've got the box, but inside of the box, there could be many different recommendation strategies which are being used. So we could possibly think of something derived off of a decision tree type model, an association rule type model, an item-based collaborative filtering model, a content-based filtering model, and so on, each of which are going to come up with their own recommendations, and then the recommender is going to decide on some kind of ordering and then generate output. So the hybridization you don't see, the user doesn't see, in the sense that those recommender systems which are possibly included inside of the box, the outer box which is seen on this figure, there are multiple different knowledge sources which are being exploited. It isn't just a single knowledge source. So if you want to see a discussion of an ensemble, which is to some degree what this architecture actually represents, go and look at the projects page, and there's a report which is included as a link off of that page. So I might combine multiple sources and ratings, which we've used extensively in collaborative filtering, both for item-based and user-based, is one knowledge source. But we may also use demographic information, and that demographic information would be available to us and usable cross-domain. So we often use cross-domain information because demographics, for example, would actually be of considerable use in both books and in movies. It should be teased out, separated possibly, and reused across the two domains. Similarly, people can be classified as different personalities, and personalities would have an effect on music choice and movie choice. And I think I've indicated on the project page that a personality-based recommender system would be something that's interesting to construct. I also have other information that pertains to that kind of modeling. However, all of these models that are user-based rely upon the construction of a profile, a vector space model. And so in some sense they have a common underlying theme. It's just that what the individual dimensions represent within those profiles clearly changes from domain to domain, and whether or not the VSM, the vector space model, can be used cross-domain. There are other content features which could be used that you can see mentioned in the bullet point below. So we can use that idea of social, and if you remember going back to the collaborative filtering slides that were early on, there was this traversal of the bipartite graph to actually find other items which had actually been rated by a user who had rated something that I had rated. And there are latent features which we can actually look at that are genre-based, for example. We can tease out that genre-like detail which you've potentially been looking at for your assignment 2 in the movie review information. And in a sense, that third bullet point, users like movies that are comedies, again, that relates to latent features, and very often we look at latent features. The final bullet point is the essence of a large number of these approaches. Common knowledge engineering effort that involves inventing good features to ensure successful learning. Knowledge representation is everything. I've probably said that many, many times, and that in essence is what the quote encapsulates, namely that we want to find hidden variables, hidden features, hidden relationships that connect the things that we see in the real world. Singular value decomposition allows us to do that. Principal component analysis allows us to do that. We didn't study that in this particular course, but it's a well-known and often used technique. And finally, neural networks are extensively used to extract these hidden representations in order to come up with effective relationships that will allow us to predict, classify values, ratings in our recommendation domain. So augmenting features, we can essentially invent features, and a large number of techniques were talked about. The bipartite graph that I mentioned on the previous slide is like that, but another example would be, here Alice likes 2 items, and item 7 is similar to 2 items at a certain degree. So what we can do is actually use that similarity to weight the rating of something we don't know. And what we do is we put these ratings explicitly now inside of the matrices. For example, the item user rating matrix, and then possibly project to a lower dimension, the purpose for which is to actually remove noise associated with performing this approximate evaluation of rating prediction. We can weight the ratings which we insert in these sparse matrices by how much rating a particular user does, or whether we've seen them to be historically more useful than others if we have that information. If the user has a lower or higher standard deviation associated with their ratings. All of these are things that we can do, things that we can use for initialization that may or may not have value, but it depends upon the domain. You have to do the experiments, you have to do the evaluation and modify based upon how good the resulting system appears to be. There is an example. There's a paper from 2004 by Torres and collaborators on looking at collaborative recommendations through citation use. So analyzing the references section of a paper and using that to determine ratings, recommendations as papers somebody would want to read after they had read a particular paper. So let's look at a parallelized hybrid design. So what we do is now we've got some kind of hybridization step where we are going to weight the individual recommenders which are provided, and now they receive the input directly. So previously, this picture isn't just the same picture drawn, if you will, at, with a rotation of 90 degrees. The previous recommenders were all augmented with data that didn't come directly from the user. Here, the recommenders are directly manipulating the input, and that's the architectural significance here. But now what we're doing is we're using weights at the hybridization step to give us output. And those weights can either be learned dynamically, or they can be learned statically. And the weighting can actually be dynamic as well, in the sense that I might just want to switch from one recommender to another based upon what I perceive to be the context for the current recommendation that's being requested. So let's look at weighted. So here the actual weighting of these two exemplar recommender systems, recommender 1 and recommender 2, they clearly, looking at the two boxes which are presented, would indicate that items 1, 3, 4 are recommended by recommender 1 and 1, 2, 3 by recommender 2. But now when we blend them together with a rating value as represented in beta sub k, here in the example used as 0.5, you see the output would actually be, just using the example for the first item, 0.5 times 0.5, which is 0.25, plus 0.8 times 0.5, which is 0.4. 0.4 plus 0.25 gives me 0.65. So if I do that across all of the items, you see that now I am still going to end up with 4 out of 5 of the items recommended, but you see that the ordering is neither the ordering which would actually be, sorry, it is the ordering which would actually be indicated by recommender 1, but is quite different from recommender 2. You can see that it's flipped the 1 and 2. The question is, how do we get the weights? And we can do it statically by, as it says here, empirical bootstrapping, or we can do it by some dynamic adjustment. So if we're to do it with bootstrapping, then what we would do is get the data, use different weightings, and do the evaluation across all of those different weighting sets. So the weighting sets are themselves a vector of values, beta sub k, where k is the number of recommenders. And then we would just, based upon presumably some mean absolute error, and what we might do is base that on some calculation which is shown on the next slide. Excuse me for flipping forward and then flipping back. What we might do is to use some kind of least squares fit, similar to SVD prediction, where what we do is compute the value of weightings for a model based upon how accurately that latent model with a subset of the dimensions which are predicted will actually give me the best result. The dynamic adjustment is, as it says here, you start with beta sub k all equal to 1, and then we adapt the weights to do some minimum error prediction, and we could do some least squares, some gradient descent type of mechanism for prediction. So if we imagine here that we've got a set of 5 pairs for beta values, and we've got 2 recommender systems, we're looking only at 2 items here, item 1 and item 4, then we would actually find that the value of the mean absolute error, which is computed using the formula which is shown on this slide, and it's just looking at the error which would be produced by using those weighting values and the recommendation that the combined system would produce, which is R sub I, and the recommendation which would actually be produced by the individual recommender, which is rec sub k of for the user of a particular item. So we have a ground truth, and we measure the error against that ground truth, and we can see that in this particular case that the weighting value for beta 1, beta 2 would be 0.1, 0.9, generates the lowest possible value. And we've used 5 different pairs where we've used equally weighted and then progressively less equally weighted around that particular 0.5, 0.5. And we've done the search symmetrically to give us 5 distinct sets. So the problem with this is that Rec 1 never did actually, it has rated items 1 and items 4 higher that recommender 2 didn't do. So there's a problem here in that we're going to end up possibly doing things that actually in some scenarios actually make things worse And you've got to determine whether or not those scenarios which are worse are actually more important than others. So, and if you will, scenario weighting also has to be something that you consider. So the reason that these things will work is if you have the scores that are similar across all users and items. So if you've got that, i.e. if all users are equally pessimistic or optimistic, depending on your point of view, this will work quite well. But if not, then we might need to do some form of transformation, such as we did back in the collaborative filtering lecture, where we did transforms, i.e. we removed the average. But we might want to consider things beyond the average. We might want to consider standard deviation, for example. Also, we might want to include some weighting based upon the frequency, the size of the user rating set. So don't assume that just evaluating mean absolute error across the data you've got will give you the best answer. It's possible that you may want to create data, fill in part of the matrix, rework the data that you've got until you end up with something which you consider to be of appropriate domain efficacy. I'm using that rather than accuracy because it's how good we perceive it to be, as opposed to accuracy, which is kind of a number that we will compute based upon some form of ground truth. We may, in the absolute sense, decide to switch from one recommender to another. And this is, in a sense, rather like the case where we look at the elephant and say, well, you know, the data that I've given you is actually at the moment sampling the trunk. So we really should give the whole responsibility for creating recommendations to the trunk-based recommender. And that really is rather like having weights which are used at a particular moment in time or for a particular interval of time that allow me to weight a recommender more than another for a period of time. In this case, we have some understanding that we're sampling in the trunk space of the overall model, and we should use the trunk recommender as opposed to any of the others. So basically that the beta sub k are going to be 1 for the trunk recommender and 0 for everything else. It could be that we put in place some kind of knowledge-based system that assigns the beta values, and that would be human-derived. It could be that once we see a particular threshold for below a particular value, then we may want to shift. Okay, well, this recommender was derived from a domain that didn't require a lot of data, let's use that. Basically the second bullet point just says we might want to do something else. It doesn't really say very much. But this is a meta level design. So it's a design of a component that, if you will, sits outside of the recommender 1 through n, which are all receiving the input and then providing the data to the hybridizer output. That would be kind of a model which feeds into that hybridization output piece. And could well be rule-based, could be a decision tree, could be an association rule, could be something else, could be a neural network, who knows. Another way of looking at this is to say give the user everything and let them decide. And so you can see here that what I give you is the score associated with a particular recommender, and that's what you get. So you just perform the union and give them everything, but presumably ranked. But one would hope that the scores are all derived from the same domain, because it doesn't make much sense to rank based upon score unless the scores are all derived from the same domain. And this is a user interface thing. You might even provide the user with some kind of sliders on a screen that allows them then to provide their own kinds of weights, as opposed to just assuming that the weights are correct. And in fact, if you allow them to put sliders, you could use that feedback in order to derive values which you could use in some kind of computation of automated weighting. So sometimes if you allow feedback based upon this hybridization approach, you can still actually change the way the system works going forward, but you're always allowing the user to select everything as opposed to providing a filtered view, which is what the previous approach would tend to do. We can also pipeline things. So here we've got the actual recommendation that allows one recommender to feed its list, if you will, of recommendations to the next recommender in the pipeline. And optionally, you can allow the input to be fed in as well. So here you can see that recommender N and presumably all of the intermediate recommenders also get the input, but that isn't necessarily the case. You could actually have recommender 1 providing a list of recommendations which are filtered by recommender 2, and then 3, and then 4, and then 5, and so on. And the idea is that the cascade model will actually refine or filter the output to the user. This is not dissimilar from the idea of the dialogue interaction that I talked about in the previous lecture, where you saw that the recommendations were being refined to a subspace based upon a dialogue. Here, that dialogue is replaced by the recommender pipeline which precedes it. That's what's going on. And ultimately, what is recommended comes from that subspace that is being rated. But the recommender N here, which provides the output, can be more sophisticated. It can mix and match, if you will, from a particular subspace, whereas the dialogue system is meant almost to, if you will, fence off parts of the subspace based upon the specification of thresholds of one or more particular dimensions of the variables which can be set values to. So the model is quite simple. The cascade model just says the successor's recommendations are restricted by the predecessor. So then a recommendation for the kth recommender can only be the recommendations from the k-1th recommender, or they can't be recommended. That's all it says. It's not particularly interesting. The recommender can never introduce additional items. So the size of the set of recommendations at a particular point in the cascade will always be smaller than or equal to the number of recommendations that were made at the previous point in the cascade. The idea here is that we are very precisely refining what is presented to the end user. So it's continually reduced, And the idea is that we get rid of things which couldn't be of interest. And so very often you will see a constraint-based approach applied early on, and then we use some kind of model-based recommendation which is used later. And so you can see that collaborative filtering is mentioned for the second and subsequent. So you may not even assign a score in that first recommender, but the idea will be knowledge-based, and that knowledge-based may actually be derived from actually a set of if-then rules, decision tree, for example, perhaps, or an association rule. The idea is based upon the history, either of the collective or of the individual. But either way is that the refinement occurs with a model-based view, having already thrown away things that are probably not of interest. So we might use this association rule for filtering. We might use the type of model that I showed you in that knowledge-based engine that's shown as a bullet and for you to play with in the previous lecture. So here's an example of a two-stage cascade model where recommender system 1 is actually assigning scores, but the importance here is simply binary. An item is either recommended or not recommended. The score that is presented to the end user comes from the second recommender in the cascade, recommender 2, and you can see that the only recommendations which can be made by 2 are items 1 and 3, items 2, 4 and 5. Sorry, items 2 and 5 were removed by recommender 1. Item 4 is removed by recommender 2, and so the recommendations which are produced by recommender 2 are items 1 and 2, which now are ordered item 1 and item 3, but were recommended to have been used on its own, item 2 and item 1 would have been recommended in that order. So you can see now that we have got a different ordering of items for recommender 2, which would actually have been generated distinctly from recommender 2 on its own. So the recommender 1 just did a filtering process, recommender 2 did the ordering and refinement, and you can see that the ordering which is absolutely generated by the hybrid is different from the recommender 2 on its own. So it's also possible to use a recommender that uses a model built by the predecessor. So if you will, I'm generating a matrix that is generated by the predecessor or some model. It doesn't simply have to be a set of things. It can be a set of things that have more information associated with it. Examples here, because there's a very large number of possibilities here, is that this particular example, some kind of fabrication of a model, is that you've got a content-based recommender that's going to generate a user model using some form of vector space model that's going to extract from the content it's presented with, and then the collaborative filtering portion of the recommendation system is going to extract similar peers and then use a recommendation based upon the ratings of similar users. We could also use some form of constraints that are implied by a model which we've extracted from the domain. Again, that could be association rule based, it could actually be decision rule based, and then some kind of knowledge based component after that will actually do the ratings. And both of those examples are real. But what is past now is actually a set of things, possibly with extra information, that in the first case we've derived a vector space model associated with the input, and in the second case we have extracted, for example, a set of features that we need to have satisfied in order that we can actually proceed. So sub-bullet collaborative filtering learns a constraint-based could actually be the application of the knowledge-based engine that I showed you in the previous lecture. Lots of limitations, lots of different things can work well, not work well. This slide basically says try it out, look at what's been tried before, and make a determination upon what works. The fact is that recommendation systems really is one of these domains for data science where the result justifies the means, nothing else. And I can't say more than that. Netflix, the 2006-2007 competitions, they used some form of stacking. They did use this kind of approach of user modeling and genre, the extraction of models other than just the raw ratings in order to come up with effective models that came up with better recommendations. The identification of latent factors based upon reviews and ratings, and ultimately that earned somebody $1 million. This is the literature that I've pointed to in this particular presentation. There's lots more recent than 2004. It's a very fertile area. The review document, which is highlighted in the collaborative filtering set of notes, is a great place to go for recommender systems generally. And I think if you did a search on hybrid recommendation systems and the keyword survey, you'd also find things that are very, very rich. Anyway, that's all for today. Thank you.